So here is a slightly outdated version of the sunspot number. Has been a lot of recent work updating. There are some inconsistencies here. These modern times that seem to be higher than anything else possibly respond to actually an overestimation of sunspots in the modern times. So, but in any case, here is the period that Schwabe observed, right? He looked at the sun to this time. There had been observations of the sun before him, but no one had really put together the fact that the sunspots would change in decadal timescales. So we have alternating peaks in solar activity maxima followed by quiet periods, right? What that we call minima. And this time variation is predominantly cyclic with a mean period of 11 years, right? Now, as we saw yesterday, sunspots are associated with regions of very strong magnetic field. And this is an image taken by HMI. And when I show you the magnetogram associated with that, then you can clearly see, so the yellow and red is magnetic field that is going towards you. So it's a radial magnetic field that goes out of the screen. And the green and blue are magnetic field that is negative, that goes into the screen away from you. And so you can see red and blue indicate the presence of very strong magnetic fields, actually. So it's a very nice color scale that they use. And you see that it has a very nice match with sunspots. And now, these regions are called active regions. You may recall from yesterday's lab, actually, when you were asked to identify what makes an active region an active region. So there are these bipolar structures that appear in the surface of the sun, and they have a very interesting set of kind of global systematic properties that are actually very important for understanding the cycle. So I'm going to go through them several times. This is the first time that I'm going to introduce them, although I'm not going to use them much in this actual lecture, but is the fact that they present a systematic orientation and tilt. So if you look at these active regions in the northern hemisphere, you see that the positive is generally closer to the right limb of the sun, right? That's the sun rotates from left to right when we look at a movie. And so that is what we call the leading polarity. The negative in the northern hemisphere is closer to the left limb of the sun, the trailing polarity, because it goes behind. But if you look at the southern hemisphere, things reverse. So now it's the negative, the green one, that is closer to the right limb, and the positive, the one that is closer to the other limb, to the left limb. I'm using right and left because east and west in the sun are reversed, and so it's a little confusing sometimes. Now, if you trace an arrow that goes from one polarity to the other one, then you can see that this east-west systematic orientation of active regions. This is actually pretty robust. There are exceptions, that are what we call anti-Hell regions. The other thing is an inclination with respect to a line that passes through the equator. So there is an angle. These arrows are not perfectly east-west. They have a north-south component. And this inclination it has a lot of scatter, so I will show you later, but generally makes it so that the leading polarity, the one that is close to the right limb, closer to the right limb, is closer to the equator, and the trailing polarity is closer to the poles. So you can see it in these arrows here. So the most visible feature of the cycle are associated with active regions. And here is a nice movie that shows that. This is a magnetogram again. The yellow is positive, that is going towards you, and the blue is negative, that is going away from you. And the first thing that this movie does is create what is called a Carrington map. So you take the central meridian in the sun and stack it in time to have like a 360 degrees view of what the solar surface does. And then when you see it evolve in time, you see that their numbers change with the cycle. So there is a very clear difference between minimum and maximum. And then you have this very clear migration of the place where the active regions appear with the cycle. They first start closer to the poles, and with the cycle, they move, the place where they emerge moves gradually closer and closer to the equator. The lifetime of an active region is maybe a month or like a couple of weeks. So this is more like the place where they appear, rather than an actual movement of the active regions towards the equator. So this is very nicely captured in the magnetic butterfly diagram. So if you take each one of the frames in that movie, average it in longitude and stack it in time, you have the butterfly diagram. So you can see the migration of active latitudes, right? The place where they appear. There is polar migration of the decay diffuse field. And there are reversals. So I have shown you that there is a reversal across the equator. So the polarity reverses across the equator. There is also a reversal from cycle to cycle. So normally when we talk about a cycle, we're generally thinking it in terms of an unsigned quantity. So the sunspot cycle 21 and the sunspot cycle 22 and so on. But the magnetic cycle, really strictly speaking, is 22 years, right? You have to go through a full reversal to go back to the point where you started. Okay, the cycles are not unique to the sun. You can see it in other stars. And this is a very nice result that is a compilation of several surveys during the last 40 or so years of a solar analog. So this is a star that is similar to the sun in many ways: age, rotation, size. And so here, what you're looking at here is what is called an index, the S index, and it's kind of like the relative strength of specific lines, like emission lines, to the background, to your black body radiation. And it's generally, it's basically an indicator of the presence of magnetic fields in the star. And so you can see that there is kind of like an oscillation that goes up and down, right? Here is a similar index for the sun. So this is another index, another K index that is also kind of one of those ratios, looking at the sun as a star. So you can see there is a significant amount of scatter, as you see here in the star as well. I don't know if, oh yeah, luckily in this screen it's actually quite visible. So, but of course you have a much better cadence. You can see that there is significant gaps in the observations to these stars, because these stars, people look at them for, for a week, and then look at other stars, and a couple of months later or something come back. And so, but basically, so the dynamo, these dynamos are not unique to the sun. And so what I wanted to do in this lecture is kind of make an introduction to the dynamos in general without a very necessarily like a very strong application to the sun. That's something we will do in the other lecture. So it comes now, time comes to the introducing the stellar dynamo. So what is a dynamo? The original dynamo is actually it's a machine that converts kinetic energy into electric energy by moving a conductor inside a magnetic field, basically. Wikipedia to the rescue, right? When we normally talk about the dynamo, we're referring to the original Faraday's dynamo, where he had this metallic disc that passes through a magnet. So it's kind of like a magnet that has positive, negative, and then the disc is inside. When you spin it, you end up creating an electric field from the edge of the disc to the interior of the disc, and that if you connect the edge of the disc and the center of the disc to cables, then that electric field drives a current, right? So you can use that to convert that mechanical energy into electrical energy. However, the solar dynamo and dynamos in stars are much more similar to the kind of generator that we normally use. So it's not the traditional dynamo works by having particles that are moving inside a magnetic field, right? So it's kind of like a game of reference frames, which also happens in the sun. But the sun, it's more like this kind of generator, that what you have is a changing magnetic field in a loop, in an electrical loop. So when you have a magnetic field that changes, and inside the loop, basically you have magnetic induction. And so that's the way our power plants work, right? So we have the water or steam that drives a turbine, and you have this plane, like a set of coils that spin inside a magnetic field. And the fact that the thing is spinning makes it so that the magnetic flux inside that circuit changes in time and drives this current, an alternate current, right? Now, inside stellar dynamos, things are much more complicated because the shape of the current loop can change freely. So now you have freedom as to you don't have this set this set square, but the square can change in shape, right? And can alter itself to basically create like a feedback loop that leads to the creation of very stable magnetic structures. Because now you have also your conductor is a very, very, very good conductor. Now the magnetic field restricts the movement of particles. And so now you no longer have the traditional magnetic field that we always think it's kind of like an invisible field in space, but you actually have a massive quantity, like object, so the plasma combined with the magnetic field now becomes like a different entity, right? And so now the evolution of the magnetic field has inertia, and so that makes it so that the magnetic field is kind of elastic in behavior, and that's why I chose the silly putty, because it's kind of like has this kind of elastic properties. And the other thing is that the magnetic field is used to induce the magnetic field induces the currents that it needs to exist. So now you have this kind of like chicken and egg kind of problem, that you have a magnetic field that induces the currents that it needs to exist, but its evolution induces other currents, and so it alters itself. And so this brought me this is a very nice mythical creature you may have heard that is called Ouroboros. So it's a serpent that eats its tail, but eating its own tail nourishes it. So the thing never dies, right? It's always eating its tail, but it's always growing. So it just goes around and around in circles. And so this is, next time you're going to see a tattoo here, I'm going to have a tattoo of this serpent. Okay, so now we're going to do through the basic necessary steps for a safe and fulfilling dynamo experience, and this is where we're going to use our silly putty. And yesterday, Sarah told you that the dynamo was like a dance, and I just cannot believe that I never thought about it in terms of the dance. I actually thought about it in terms of earthquake safety. So perhaps next time I'm going to talk about steps in a dance, but for today, I don't know if you have ever seen these posters that when there is an earthquake, you need to drop, right? Cover, hold on, and take a selfie. And so that's kind of like what we're going to do, but with the solar dynamo. So now take your silly putty, make it like a little snake. It doesn't need to be super long, and then close it to form a loop, right? Thick is better than thin, so it doesn't need to be, you can make it as small as you want. And so the first thing for having a dynamo is that you stretch, right? So going from something like this, then you stretch your magnetic field. And this is done by flows generally, right? So you have you can have turbulent flows or large scale flows. This is what changes your magnetic field, right? So you stretch it, you twist it. So now there is, if you imagine that the only thing that the silly putty doesn't have right now, I need to see if I can come up with a way, is direction. But if you look at here, this image, then you can see that now you have the magnetic field is going into this kind of H shape. And then you fold it, right? So now you have a structure that there's kind of like the same original size, but you have twice the amount of flux, right? So that's basically that conversion of kinetic energy into magnetic energy. So it goes again, right? You stretch it, you twist it, and then you fold it. And now you have 4 times the amount of flux. And if you do it once again, then you stretch it, right? You twist it, and then you fold it. And now you have 8 times the amount of flux. And now you take a selfie. So take out your cell phones and make a selfie, if you want, and upload it to the Facebook page. Yeah, yeah. So I'll give you 2 minutes to decide whether you want to take a selfie or not. Okay, so how does this work for the sun? We're going to do a 3-dimensional stellar dynamo simulation now. So this is a state-of-the-art at this basically you can do, right? And to do that, first I really introduce you to this very, very important concept when you think about dynamos, which is the concept of the poloidal and toroidal fields, okay? This is like whenever we talk about dynamo, we always talk about the poloidal and toroidal fields. So this is super important. And you will see it in your lab. You will see it in the rest of the things that I'm going to talk about. So take these concepts really deep into your heart. So poloidal and toroidal fields are kind of perpendicular components of a spherical magnetic field. Poloidal component is contained in the r and theta plane. So a typical example of a poloidal magnetic field is your typical magnet, dipole magnet, right? You have, this is an axisymmetric magnet that has no phi component, and all is on or r and theta. Toroidal is the phi component of the magnetic field in spherical coordinates. So it's perfectly perpendicular to the poloidal field, and it's like a torus, right? So the solar cycle is a dynamo, a cycle, a stellar dynamo is a process that takes the global configuration of the magnetic field of the star between these two, poloidal to toroidal and back. Okay. So now it's time for us to do our silly putty. So this now here is better if you work in couples, like in pairs, rather than as just alone. But you're welcome to work alone if you're not sitting beside someone. So now you have here that you have a poloidal field that is embedded in differential rotation. So in the sun you have different layers rotate at different speeds. Near the surface, you have an equator that rotates faster than the poles. And what we're going to simulate is one of those field lines. So just make a line. Don't make it just like a straight line. This is your poloidal. This is a poloidal field line. Make it, we're going to abuse this line quite a bit. So it's better if you make it thicker than thinner, right? And so this is when it's useful to have a partner to work with, because you're going to wrap it around your finger, right? Your finger is going to be the axis of rotation. But you're going to do it the solar way. So you're not just going to do this, because this is not the way it works in the sun. In the sun, you have an equator, so the middle of your finger is what gets ahead. So you basically, your field gets, the middle of your line gets ahead of the ends, because the equator rotates faster. So when you wrap it around your finger, I guess it's useful to do like a V. Oh man, this is art. And then you wrap it like this so that it goes around your finger. But the important, one of the things that I really want you to notice is that once you have, it has it starts on one pole, it wraps in one direction, then it turns around at the equator, and then it wraps in the other direction. Okay, so I think I think you should do it in pairs. So just take a minute, and I can. Just take, okay, perfect. So take a minute and wrap the thing around each other's finger, but do it the solar way. And then when you have it in your finger, just let it wrapped around your finger. Yeah, exactly. That's beautiful. Yeah.
The silly putty tends to want to reconnect.
Oh, yeah. Well, although this is not reconnection because you have the magnetic field is all pointing in the same direction. So it
The magnetic field is all pointing in.
Oh, yeah, not across the equator. It's true.
Okay.
Not across the
Okay.
equator.
Yeah.
Not across the equator.
Right in the middle. It starts. Yeah. Okay. Well, yeah. So we have.
Now, the first thing that so this stretch basically multiplies the amount of flux that you have. So this is, you put energy into the stellar dynamo this way. Now, the other thing that I wanted you to realize is that just because and I guess this is the case of the sun, you have differential rotation and you have a change in polarity across the equator, then you can see why when you have active regions at the surface, there is, in one hemisphere, they're oriented in one direction, and in the other hemisphere, they're oriented in the other direction because their origin are these toroidal fields. So you see in the surface of the sun, you see them oriented east-west. That's because they come from this east to west magnetic field. Okay, so now we did this stretch. Now we have the twist. So here is the tricky thing. Now you need to pinch your field, and then you need to stretch it and twist it so that it's now perpendicular to the toroidal field, and it's poloidal now, right? So do it in both hemispheres. And now this is the thing. In one hemisphere, you're going to twist, whatever, you choose what you want. You twist it clockwise. But if you did that in one hemisphere, in the other hemisphere, the twist is counterclockwise. So now, because a huge component of this twist, it has to do with Coriolis force, right? So this is driven by, I'm going to tell you what kind of mechanisms produce this kind of twists. But one important thing that I want you to realize is that the twist in one hemisphere is in one direction, and the other hemisphere is in the other direction. So this basically, the fact that you have twists with opposite polarities cancels the fact that you have reversal of polarities across the equator. So you basically are twisting things so that when you go north-south, they have the same north-south component, in a sense. Okay, so now you have something that looks like this, which is just exactly like the picture that you have there, right? So and also, yeah, take a time to follow with your finger your magnetic field to kind of have a feel for the direction it follows, so the kind of the polarity orientation. Okay? And then the last thing is fold. But actually that's not true, because you can also reconnect. And so, and really in the sun, you have these small scale magnetic fields, which are these kind of twisted loops. And then you reconnect them, which is basically, you can just bring them together and try to erase the line between them. But now you have a large scale poloidal field, right? So now you have gone from a large scale through the creation of these twisted folds and the reconnection, you have created a poloidal field again. So this is your three-dimensional stellar kinematic dynamo simulation. So take a selfie. Take a selfie with your great dynamo. Okay, so now I told you that there are different, so now try to go back to your wrap around your finger kind of thing. Now you can just wrap it around, just do like this. You're doing only one hemisphere, okay? So now you can just wrap it like this. You can have this kind of twist into the poloidal plane in small scale or large scale, right? You can have small scale and local. So you basically are pinching very small everywhere. You make these very small pinches, right? So by making it very small pinches, but many of them, you're basically creating this large scale poloidal field, right? This is traditionally in the dynamo language, or you can have a large scale pinch and twist that is almost like if you have your toroidal field, and now the thing just goes towards the surface of the sun and twists. But it's a very large scale thing that spans the entire convection zone. So that's a large scale and global. Both have the same effect. Both have the same effect of creating net poloidal field. The small scale is basically helical convection acting on the magnetic field. We typically talk about it as the alpha effect. So when you hear the alpha effect, this is what we're talking about. And it's just the fact that you have upflows and downflows that are subject to Coriolis. So what happens is that the upflow kind of twists, it makes like turbulence upflows do like this, and the downflows, it's like a double helix. They go the other way because you change sign of your movement. And so that's kind of like what imparts these twists. It's limited by the relative amount of energy available in convection. So you have, when your field becomes too strong, the convection, this turbulent convection cannot really affect it very much, okay? But you can also have Coriolis force active on rising big flux tubes, which is the large scale. And these actually are the flux tubes that, since they have this shape like a U, from the bottom of the convection zone that is here to the top, produce your active regions. Is you basically just make a cut like this, right? You have a positive and a negative, right? And so that is the active region. So that is known as the Babcock-Layton effect. But this is limited to strong tubes. So you have to have very strong flux tubes so that they become unstable and buoyant and rise to the surface. So you have these competing things. And one of the things that we're going to look into the lab is how do dynamos that are driven by one effect or the other look like. Later, we will talk about what is going on the sun. So finally, then you have different ingredients that basically are what move all these fields around. So I'm going to go very quickly through this. You have differential rotation. So this is actual measurements of the differential rotation of an equator that rotates faster than the poles. There you also have shear, so difference in speed, rotational speed in the radius. There is a layer of very strong shear at the bottom of the convection zone. So all this is what can help you twist your magnetic field around. Main source of energy. You have a meridional flow. So this is something that helps the cycle. It gives some of the timing to the cycle, and because it moves things around, it helps with this reconnection of the twisted flux tubes that you're creating. These are the latest measurements of the meridional flow by two different groups using two different instruments. I forgot to include one. So it's a flow that we have believed to be very important for our models, but right now we're kind of like a bit of an identity crisis because we're getting the first deep measurements of meridional flow, and they're not exactly what we expected us to be. Well, one measurement says that they are what we expect them to be. The other measurement says that they're not, and so we need to figure out that. And it has a strong cycle impact on cycle period. Turbulent diffusion, so the interaction of turbulence with with your magnetic fields. So the fact that these things live in this turbulent convection actually shreds pieces of your magnetic field away, right? Takes pieces away and then makes separate tubes. And so it erodes away your things. And here is another movie showing you kind of like the interaction of the magnetic field with those things at a small scale. So you have this, each one of these positives and negatives is kind of like a little flux tube that goes, and it's connected, positives are connected to negatives, and you can see that they're shuffling around, being shuffled around by turbulence. So turbulent transport is not only diffusion, there is also other things. Here is like a snapshot of an active region. Every time that it comes around, one rotation, like 1 month later, and you can see that it appears here, and then it's kind of spreads around, so it becomes like it just basically goes away, and so. Pumping is another consequences of the fact that your turbulence is asymmetric. So here is a movie showing you just turbulence, right? You can see that there are big bright blobs surrounded by dark boundaries. The big bright blobs is hot material, so that it's less dense and it's hotter, so it looks brighter, and occupies more volume than the narrow cold downflows. When the things cool down and then go back down, but they have cooled, so they're less dense, occupy less volume, and so you have this narrow, fast downflows. And then when you make kind of like a three-dimensional cut in a simulation, everything that is blue is going up. Everything that is red is going down. You can see this asymmetry, right? There is more area covered by blue than it is covered by red. And that is basically the fact that you have this asymmetry. And this conserves mass because you have different densities with different volumes, but it's more efficient. You have a more efficient transport of magnetic field downward because the magnetic field kind of has inertia, right? If you have fast flows, that kind of pins down your magnetic field and brings it down. And so you have this net transport. Okay, so the final thing that I wanted to talk about in this lecture, in prep for the lab that we're going to have, is how a dynamo, a stellar dynamo, it really works through the balance and counterbalance of competing effects. So the simplest model that we use to understand the stellar dynamos, and the one that you guys are going to be using in your lab, is just based on the induction equation, the MHD induction equation. And you basically have that the evolution in time of the magnetic field depends on the way the magnetic field interacts with velocity fields with a process of turbulent transport, right? Diffusion and transport. And this alpha here is that twisting, that helical twist of your fields. So your flows are, as I mentioned, the differential rotation and the meridional flow. Turbulent transport can be diffusion or pumping. So, and you have poloidal sources. So basically this twist of the toroidal field into the poloidal plane. So when you got your last copy of Dynamo Fighter 2, right? For your Super Nintendo, and then you load it up, and then you choose 2 players, and you go to the selection screen, okay? So you have here all the ingredients that I mentioned: the differential rotation, meridional flow, diffusion, turbulent diffusion, your twist, your poloidal twist, and your turbulent pumping. And so if I tell you, okay, we're going to see a fight between magnetic sources and decay. Can you tell me? So I'm going to do the easy one. Decay, of course, is turbulent diffusion. So what are of these ingredients do you think act as sources? Sources that basically put energy into the system. Sorry? Differential rotation, and there is another one. remember that, so differential rotation turns toroidal into poloidal field. Convection, yeah. So the basically, yeah, the other thing that closes the cycle, the twisting, right? And so you have like this fight. And this is going to tell you whether your dynamo survives or not, right? If you have diffusion that is too strong compared to your sources, your dynamo dies, right? So the other kind of fight that you have when you try to understand how the dynamo works is advective versus diffusive transport. So I told you again, well, I gave you the answer. So you have diffusion on one side, and on the other side, what ingredients would you put? Something that just moves things around. Sorry? Meridional flow is one, and the other one? Differential rotation, but yeah, but the differential rotation is more like a shear source, I guess. So I guess if you all cannot use differential rotation, what else could? Yeah, turbulent pumping. So those are basically diffusion versus advective transport. So this turbulent pumping, the fact that you have asymmetry between upflows and downflows are moving things around, and meridional flow is also moving things around. So basically, the way we quantify these fights and who is going to win is using what we call dimensionless dynamo numbers, right? And so dynamo numbers are basically what characterizes the fact that fight between sources and decay, and you can have two, right? One that is proportional to the strength of your differential rotation, which is normally used like denoted by an omega, and diffusion, which is denoted by eta. And the other dynamo number is actually your poloidal source, which is alpha, how strong your alpha effect is, for example, and how does that compare to diffusivity. So these are the things that you're going to use in the lab to basically kind of get an idea of the differences between the different dynamos that you're going to be looking at. And the other one are called Reynolds numbers, and it's basically ratios between speeds, characteristic speeds, and turbulent diffusion, right? These, as you see here, these have other factors so that they become dimensionless, truly dimensionless. But generally, it's like this proportionality. So you have always source versus decay is one kind of number. Advective transport against diffusion. So that's basically it. That's what we're going to do in the lab. So now for this is basically the last, like this last slide is a summary of this 45-minute, I hope, 45-minute lecture. Differential solar and stellar cycles are magnetic in nature and are powered by a dynamo mechanism. Differential rotation, helical turbulence, and the twist of emergent flux by Coriolis are the main mechanisms that keep stellar cycles going. And the relative importance of the different mechanisms involved in magnetic field generation and transport is what determines the exact characteristics of your dynamo. So, thank you. I don't know how are we too much behind?
We're going to take questions.
Okay.
Quantity eta, turbulent diffusion, how do you quantify turbulent diffusion?
So, experimentally, what you do is you look at concentrations of flux, and then you see how far apart they get with time. And you kind of model that as a process of diffusion. So kind of like following this process around, right? So if you know that at day one you had, unfortunately this is a GIF, you have this active region here, right? And 1 month later, it has been spreading out, right? So you kind of try to peg a number on that quantity. What will make such a concentration of flux spread so much after so much time? Other questions?
What's the magic of the sun that is 11 and 22 years? Is that meridional flow?
So yeah, there are one thing that is very important is the actual physical size of the sun. So how big it is, how deep is its convection zone, because ultimately that sets the stage for transport. And then the rest indeed is transport. So how do you connect the different layers in the convection zone? So how strong is your pumping? How strong is your meridional flow? How strong is your diffusion? Because diffusion also transports things around. And the interplay of all those things sets your period. So, and this is something that you will see in the lab. If all these three quantities, pumping, diffusion, and meridional flow, have impact on the period, if you leave all the other ones static and don't change it, then you will see period changes when we change one of them. So it depends on how they interplay, how they work.
There's the tachycline view of producing these strong fluxitudes that you show virtually. But then there's the more generally convective dynamo view that says you can have coherent bundles of strong field forming in a more turbulent convection zone and erupting. Does your picture care which of these things is actually correct?
Okay, so I'm going to repeat the question, and I'm going to give a little more introduction to that. When you look at the differential rotation, I mentioned that you can see what is called shear. It's a difference in rate between different locations, right? The latitudinal shear is one of the first things that people measure, and you actually see it when you look at sunspot measurements. Is the fact that the equator rotates faster than the pole. But then, I don't know, in the 90s, people were able to measure the meridional flow inside the sun. And we realized that there is actually a place where we have very strong radial shear. So now there is the difference in rotational speed between the radiative zone and the first layers of the convection zone is very strong. And so there has been a lot of debate about which one plays where exactly do those toroidal fields that you wrap around your fingers live, right? Do they live inside the convection zone proper, and do they mainly interact with latitudinal shear? Do they live at the bottom of the convection zone, and they're basically this conversion an injection of energy in the dynamo, does it happen at the bottom of the convection zone? And there are other things that also play a role in making kind of those an educated guess about where the seat of the dynamo is. For example, if you believe that active regions are these flux tubes that are pinched from the toroidal field, then and you need a minimum amount of field strength and flux to be able to have them, where can you store such strong fields? And so on and so forth. So there has been a lot going on, and the question Janet asked now is, where do I think it lives, right? So do I think it lives here at the bottom of the convection zone? Do you think it lives inside the convection zone? And the thing is that you can, since you have several processes by which you can take toroidal field and turn it into poloidal field, there are dynamos, stellar dynamos are viable, whether you live in the convection zone, whether you live at the bottom. So it's not a clear cut, like there's no question about this, it lives here or there, right? I have to say I'm not completely sure. Because you have detailed simulations of the magnetic field show different things, and so my general feeling is that you have magnetic field living all over the place. You cannot. It's not like one layer exclusively or the other. My belief is that these big bundles are indeed stored deep inside the convection zone. So you have a lot of flux at the bottom of the convection zone. That's something that I do believe is taking place. But I think that a lot of that flux comes from inside the convection zone itself. So it's not like like all layers are playing a role in a sense. Pumping this downward net transport of flux takes fields from the convection zone and brings it down to the lower bottom. But the whole interplay is taking place all across, I guess. That's what I would say. But since you cannot really have observable signatures of this, and the kind of models that I work with are phenomenological, so you cannot use them to prove a point. You have to assume something. And so I guess I can only answer with this question with my assumption, but I cannot give you like... Carol?
I agree with what you said. I think you could add one statement though. The bottom of a convective envelope is not a necessary ingredient, because there are stars that are fully convective and they power a dynamo. What probably does happen is that they can change the mode in which the dynamo operates. Yeah. But the converse as to answering where is the solar dynamo,
I don't know.
more funding.
Yeah, so this is an interplay. The meridional flow, it like very short, mainly is conservation of angular momentum, right? So you have the fact that you have a rotation rates that are different at different layers, right? The fact that you have kind of like viscosity in your turbulence, and the fact that you have to conserve angular momentum all play together to transfer kind of torques and forces across that lead up to the creation of the meridional flow. But that being said, our simulations, detailed simulations of convection and stellar convective envelopes have found that the meridional flow is a very sensitive flow. So you can change things slightly, and then the properties of the meridional flow can change. And so it's a delicate balance between that. And it may be that actually magnetic fields, since they have inertia and they have like integrity, so you can you can use them to transfer stresses, right? If you have a field line that resists stretching, and is cohesive and keeps integrity, it basically kind of like works as a mortar for the convection zone, and so you can also use that to transfer angular momentum and so on and so forth. So it's a combination of things that unfortunately is not like super clear cut. Lika?
So what funding was mentioned, I kind of want to understand. I mean, what are you looking in order to, this is a very important issue, to resolve the issue. What is needed? Is it a newer kind of observation? Is it more, parametric study, modeling, analysis? How would you come to a closure on this problem?
Oh man, this is just such a difficult problem. I'm super in the spot here.
I say I feel like it's a combination of all of them. We really need better observation, more observation, and we need more modeling. We need all of those components.
I think,
Because asking of what? And I
yeah.
would say that we need to make use of the stellar population, because that's the only way in which we can do a parameter search of all the necessary ingredients. If we don't combine it with high fidelity magnetohydrodynamic simulation
yeah. I think that,
Are ready to provide funding,
yeah.
let's say. I want you to define. That's
Yeah.
all important.
I think,
Topic, I do solar stellar connection. We have observation.
I think that, okay, so now that I have had a little bit of time to think, I think how to say, like more, for example, yearly workshops where people from different things can come together and have and discussion, like somehow encouraging collaboration across the different disciplines. For example, one thing that it's very important for us is the Meridional flow, right? Funding so that these people can get their act together and figure out and agree, right? I'm as a modeler need to know whether I can keep using this one or I need to basically start using this one. But as long as there is no agreement here, I'm still with the freedom of choosing, right? So for example, initiatives where you can have coordinated efforts of heliosysmic reduction of specific sets of data, specific instruments, something like that. So to kind of like provide funding so that these people get together and figure this out, for example, can be very useful for us to basically further improve our understanding. Also, really to enhance the dialogue between the different kind of modelers communities, right? Surface, interior, phenomenological like me, flux, understanding exactly how active regions and so I think that perhaps in this moment, I guess we need to talk more, I guess. That's what I will say.
Okay, I mean, I throw a challenge at you that you figure out as a community what you need and then come state that. And
The other thing of extreme value, I think, is that this particular problem is one that has a time scale of a decade. So
Yeah. Oh yes, that's the other thing.
So long-term
Yeah.
records of diffuse stars that have been monitored.
Yeah.
Those possible, we start over.
Right. So I think it's super important to keep Solis. This is NSO, so I'm not necessarily addressing you as a, but just you as a part of the funding, like agencies, communities. I think that one thing that is severely lacking in our community is a long-term vision, long-term programs, surveys that are long. It's extremely hard to do this in the United States because people are always craving the, bang, 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 bang. Okay, I sent an instrument to whatever, Venus, and it's going to just plummet through the atmosphere and it's going to give us such many things that we have never seen before, and it's going to do it in 3 hours. Okay, and we're going to have a science paper 1 day later, and right? What we need to really understand is long-term commitment. And this is actually this is the amount of funding that is required is very low. So keeping historical records alive, making sure that there are instruments like Solis that are always working and will work until we're dead, basically, these kinds of things are
that's all that is happening.
Yeah.
Right now you have the observation, you have ability to propose, you have to give us a strategy that we follow.
Okay.
Otherwise it's just ad hoc funding that's not leading to the closure.
Okay.
So I want to understand if this is a really important problem, give me a path that leads to closure with the present observational data that we have. And then you can mention the future, that we get long-term data, etc. Absolutely important.
Yeah. You really put me on the spot here. Yeah. No. No, you put me in a difficult spot.
Yes, challenge in general for the next generation.
Right.
The opportunity is tremendous because this is another one of these fields that shows just how wide-reaching heliophysics is. We can and have to combine all the way into the stars to understand that particular problem. We can, we should.
In that respect, do we understand how far we can push helioseismology? For example, I have heard of efforts which take Dynamo models, they're in
Yeah.
There are such opportunities in experiment but they're all very subtle signatures that require many months of continuous observing before you even begin to have access to them.
Yeah.
They need to have that, there's a really strong area for progress. We're still waiting.
Yeah.
Are the planetary dynamo communities and the stellar dynamo communities completely separate because of time scale?
Yes. Yeah.
Is it the same physics, but you just don't worry about convection or?
The physics are similar. It's like you say, like there is a, but there are some properties to the systems that change things grammatically, and I think that our approaches our concepts are very similar, I guess, but I think that one of the things is that data is very different, right? And so when it comes time to compare with observations, then methods and methodology and approaches are very different. But yeah, I have never been to a planetary dynamo meeting, I have to say.